Okay. Theoretical physicist Sheldon Cooper once said on the Big Bang Theory that I'm tearing the mask off nature and staring at the face of God. Maybe that's just what physicists at CERN got a glimpse at on July the 4th, 2012, when they officially discovered the Higgs boson. No wonder they have dubbed it the God particle. In one sentence, the Higgs boson is essentially what gives other particles mass. I will be talking about exactly how the Higgs boson works, along with some history of the Higgs boson and some background information to help you understand it a bit better. And don't worry if you completely don't understand it. I didn't understand it in 15 minutes either. Okay, let's dive straight into some history. The first idea came out in 1964 by a physicist named Peter Higgs. The problem was that two other teams came up with similar ideas later that year, and this created a big mess for the Nobel Committee to see who would win the Nobel Prize in physics for that year. But it turned out that Peter Higgs was the first one to submit this idea, and he won the Nobel Prize. And this found its way into this thing called the Standard Model, which I'll be talking about later, and that was made in the 1970s. And I will be talking about that later. And that Standard Model helped discover multiple quarks in 1995. So in around 2001, the search for the Higgs boson officially began, and it was done by the guys at CERN. And this was even before they built their Large Hadron Collider. So they really had no idea what they were doing, and they had to halt their research at 2005 so they could actually make their Large Hadron Collider. By then, they figured that CERN's rivals at Fermilab in Chicago would be the ones to discover it. But still, 7 years later, no one has discovered the Higgs boson. Now, the Large Hadron Collider is built in 2008, and people thought that it would actually create a world-ending black hole, since no one actually had made something this big before. But on July the 4th, 2012, the Higgs boson was discovered with the Large Hadron Collider. So this is essentially the Standard Model. Here's the gist of it. It was made in the 1970s, and it's a prominent way of describing how the cosmos works. You have 12 fermions there, and they're essentially, this is divided into fermions, bosons, and the Higgs boson. So there are 12 fermions, and they're divided into quarks and leptons, 6 of each. Quarks are essentially the building blocks of protons and neutrons. If you separate a proton or you separate a neutron, basically what you have are quarks building it up. And you can't go any further than a quark or a lepton. A lepton is the building block for the electron or the electron neutrino. And the electron neutrino is essentially a neutrally charged electron. And like I said before, quarks and leptons are indivisible. Now bosons. There are 4 of them. You got the photon, gluon, WZ, and the graviton. But the graviton is funny, I'll talk about it later. But essentially, what these bosons do is they mediate a force, and they carry out the specific actions of that force. Remember Mr. Olson was showing that video earlier, and he talked about how the universe had 4 forces. The strong force, the weak force, the gravitational force, and the electromagnetic force. Remember that, that'll come up a lot in this presentation. So the yellow thing you have there is the photon, and that is the building block of light. And that is because they have just enough energy to excite a photoreceptor in your eye, and it has no mass and travels at the speed of light, and that is why it's actually a building block of light. And it carries out the electromagnetic force. The blue particle you have there is the graviton. It's undiscovered because, as you probably know already, gravity hasn't been united with the other forces yet. And its existence has only been assumed. We believe that it has no mass as well, and it should also travel at the speed of light. Now the W and Z bosons, they're the ones that carry out the weak force. Then they're extremely heavy, 80 to 90 times heavier than a proton. Now, I said that each of these bosons carry out a force, right? But what does that exactly mean? Well, let me show you this example of this electromagnetic field around Earth. Every force has a field, and in this case, the source of this field is Earth. Without Earth, the field would no longer exist. And at first we thought that this was supposed to be just a wave. This field was just a wave surrounding the Earth. But quantum mechanics does not allow this. So really, This wave is just made up of a whole bunch of photons creating this electromagnetic field. And the reason I said photons rather than any other boson is because the photon is the one that carries out the electromagnetic force, whereas the W and Z do the weak fields and the gluons do the strong fields, etc. And the strength of this field depends on nothing but the amount or density of the particles that make up that field. And when you take away the source of the field, in this case the Earth, if you take away the Earth, the electromagnetic field around Earth disappears. Now let me show you an example of field theory and bosons at work. Electrons repelling. We all know like charges repel and opposite charges attract. Therefore, we know electrons repel. But why is this so? Since electrons take part in the electromagnetic force, they have an electromagnetic field around them. Therefore, they have photons around them. Due to energy fluctuations, they are constantly creating photons and then reabsorbing them almost instantly. And imagine this happening with both electrons coming towards each other, constantly making and reabsorbing photons. Eventually, one of these photons will not reabsorb into an electron, but jump electromagnetic fields from one electron to the other and be absorbed into that. So a blue squiggly line is essentially a photon moving from one electromagnetic field into another, and that force is what pushes the two electrons away from each other. Now, I've talked for the last 6 or so minutes about a standard model, field theory, and all that, but what does that have to do with the Higgs field and the Higgs boson in particular? Quite a bit. The Higgs field is very similar to all the other fields except for one major difference. It has no source whatsoever. It is everywhere. For example, if you take away the Earth, the electromagnetic field around Earth would disappear. But if you take away Earth, the Higgs field would still be there. Therefore, there is no empty space because the Higgs field would have occupied that space. But again though, this Higgs field can't just be a giant blob with this little field. So what we have are Higgs bosons that actually make up the Higgs field. Now the purpose of the Higgs field and the Higgs boson is to give mass to the fermions and the bosons I talked about earlier. The more they interact with the Higgs field, the more mass it has, and each fermion and boson interacts with the Higgs field a different way. For example, photons don't interact with the Higgs field at all. That is why they have no mass, like I mentioned earlier, and that is why they can travel at the speed of light. The top quark, which is the one with the red center on the very left, is the heaviest of the fermions, and therefore interacts with the Higgs field the most out of all of them. The electron weighs 300,000 times less than the top quark, therefore it can move much faster and have much less mass since it interacts less with the Higgs field, and even less with the electron neutrino since it is almost massless. It can almost travel at the speed of light, but it can't because it has some interaction with the Higgs fields. And basically what you see here, if you don't know already, those light blue things are Higgs bosons. And essentially what they're doing is sticking to the fermions and bosons that I talked about, and they're dragging them down, essentially giving them mass and stopping them from traveling at the speed of light. If it wasn't for the Higgs field and the Higgs boson, everything would travel at the speed of light and nothing would have mass whatsoever. Now how was this Higgs field and Higgs boson found? Well, they smashed this thing called particles and antiparticles together, and this created a giant fireball of energy. And after that, they look at the decay of the particles they made, and they look, oh, they created a Higgs boson. So we didn't actually see a Higgs boson, we saw the decay of a Higgs boson. But that's proof enough. Now, would this spell bad news for string theory? Let me iterate. There are theories out there in particle physics that the graviton that I mentioned earlier actually does exist. And they believe, like the photon, they do not interact with the Higgs field whatsoever. They have no mass and travel at the speed of light. And when the Higgs boson found, particle physicists everywhere will be turning their attention to the graviton. Now, why would this be bad news for string theory? If the graviton exists, it would renew particle physicists' hopes in unifying gravity with the other forces. And if you unify gravity with the other forces, that is essentially string theory's job. And to unite gravity with the other forces using the graviton, you will need something called loop quantum gravity. And it is a theory that it tries to achieve the same goal as string theory, but does it in a different method. Therefore, string theory would be disproved if the graviton existed. Now let me end you with a quote about the Higgs boson. For more than 3 decades, the Higgs has been the physicist's version of King Arthur's Holy Grail, Poncion's Fountain of Youth, Captain Ahab's Moby Dick. It has been an obsession, a fixation, an addiction to every physicist that almost all of them believe it just had to be true. Now let me conclude. The standard model says you should have 6 quarks, 6 leptons, and they're called fermions, and they're essentially the building blocks of the particles you learned in the 5th grade. Then you have 4 bosons. The photons, which carry out the electromagnetic force, gluons, which do the strong force, W and Z do the weak force, and hopefully graviton will do the gravitational force. And each of the bosons I mentioned earlier makes up its specific field that it carries out the force for. For example, the photon makes up all the electromagnetic fields everywhere, for example, the Earth or an electron. And if you take away the source of that field, then the field would go away. But the Higgs field is different from that. It has no source, and it is everywhere. And it gives particles mass by sticking to them and dragging them down. Hopefully this presentation has given you a good idea of what the Higgs boson is like. Are there any questions? Then